In this video, we'll be looking at completing the square. So completing the square is a method for factorizing quadratics, which is useful as it is an alternative to the quadratic formula and is sometimes quicker, as well as it puts it in a form, a quadratic in the form of the turning point form, so it means you can see what the turning point is quite quickly. So to begin with these two different type of equations. So firstly, you have x squared minus 5x plus 6. Now, you can just use another method where you can go, what two numbers add up to give you negative 5 and multiply to give you 6? So let's say negative 2 and negative 3, because they multiply to give you 6 and add up to give you negative 5. So we can say that that is equal to this, and so we can just factorize it quite quickly. If we expand that out, we can show that that is equivalent to the expression above. So you should have done this method previous years, however it's not necessary, but it is quite quick for some quadratics that are simpler and you can see two numbers that add up and two numbers that multiply. However, when you have an equation, a quadratic like this, x squared plus 3x minus 15, then the two numbers that multiply to give 15 are 5 and 3, or negative 5 and 3, 5, negative 3, and 15 and 1. So obviously these numbers aren't going to add up to give you 3, even if you change the negative sign around, so we can't just use that sort of method. So to factorize this, we could use completing the square. So effectively what completing the square does is initially we focus on the first part of the quadratic. So we focus on this part, the x squared plus 3x, and we ignore the constant for the time being. It's often best to rearrange a quadratic so it's in the highest power to the lowest power. So you can look at these first. So x squared plus 3x. So we want to try and replicate this. So in the end, the final result we want to look something like this: x squared and then plus c, a constant. It could be positive or negative. And then we want like x plus a. So something like that. Then we want to get x squared plus 3x, and we want to use x plus a squared to simplify it. Now, when we have x plus a squared, this is equal to x squared plus 2ax plus a squared. That means if we correspond that x squared plus 3x to this, we'll see that we want 2a to equal 3. We're forgetting about the constants for the moment. So 2a to equal 3. Therefore, a is equal to 3 on 2. So whatever the number is inside the squared bracket is whatever this middle term is, often referred to b in the quadratic formula, and then we divide it by 2. So what happens is we get x plus 3 on 2 squared. So let's get rid of this equation over here, and so we'll have x plus 3 on 2 squared. Now what does that give us? That gives us x squared plus 3 on 2x plus 3 on 2x, which is plus 3x, and then plus 3 on 2 squared. Now, there's no 3 on 2 squared here, but we can easily just get rid of this by going minus 3 on 2 squared. So we can say that x squared plus 3x is equal to x plus 3 on 2 squared minus 3 on 2 squared. And then if you expand that out, you'll see that those are equal. So we divide the middle term by 2, square it, then square this term we're referring to as a, and minus it from the expression to get x squared plus 3x. Now we need to bring in the negative 15 because we can't just forget about it. So all we can say is that x squared plus 3x minus 15 is equal to x plus 3 on 2 squared minus 3 on 2 squared, and then minus 15. So the minus 15 you can just add to either side there, as you can see. Then, looking down, we have x plus 3 on 2 squared, minus 9 on 4, minus 15, so convert 15 to negative 60 on 4. That's just the same thing. And we're left with x plus 3 on 2 squared, minus 69 on 4. And so that's a simplified factorized form. And we can see straight away from that the turning point, which is going to equal negative 3 on 2, negative 69 on 4. So at first it seems a bit confusing, but once you've done a few more examples, then it becomes a lot more systematic. This is just to show you how and why the formula works. So in general sense, we have x squared plus bx plus c. What we do is we divide b by 2, as you can see here, then square that term. Then we have to minus b on 2 squared to account for the constant that is produced from this function. And then we have to add the plus c there. So in a general sense, this is what is happening. So taking a question, factorize x squared minus 5x plus 1. So we'll use the completing the square method. So the first thing we do is we go x squared minus 5 on 2 squared. Then to account for the plus 5 on 2 squared, we have to go minus 5 on 2 squared plus 1, the constant. This is equal to x minus 5 on 2 squared, and then minus 25 on 4 plus 4 on 4. So it gives us x minus 5 on 2 squared minus 21 on 4. Now if you want to do it in a bit of a longer step, we can go x squared minus 5x plus 1, x squared minus 5x plus 25 on 4 minus 25 on 4 plus 1. And we can just do that because you can obviously add any number you want to an equation if you're just going to minus it, because that is equal to 0. So effectively we're summing in 0. Then we can look at this part of it, and then we know that that is equal to x minus 5 on 2 squared, and we're just left with minus 25 on 4 plus 1. So that's the same thing, but just another way of looking at it. So now that we've got this, if we want, we can actually bring this into the bracket. What we can do there is if we have, let's say, x plus a squared minus b, then x plus a minus the square root of b, x plus a plus the square root of b. When you expand that out, the pluses and minuses will cancel each of the terms apart from negative b, square root b times square root b, which will give you negative b. So what we can do here is we can say that this is equal to x minus 5 on 2 plus or minus the square root of 21 on 4. So that it's better actually to first break them up rather than just going plus or minus. So that is equal to x minus 5 on 2 plus the square root of 21 on 2. So the square root of 21 on 4 is just equal to the square root of 21 on 2. X minus 5 on 2 minus the square root of 21 on 2. And that will expand it out. And that is useful as you can then find out what the x-intercepts are. So if you can get this, you can find the turning point, then you can sub that in, and if that's an easy number, such as minus 9, so we can just go plus 3 and minus 3, we can therefore work out what the x-intercepts are, and it's easier to graph.